Today, getting you started with a little nuclear chemistry. The first thing here, just some review of what an isotope is. So isotope, atom of the same element, having different mass numbers. So to be the same element, remember that you need to have the same number of protons. So hydrogen all the way across, and that's because it has one proton. To be an isotope, then to change the mass number, you change the neutrons. So hydrogen 1 here, hydrogen 2, so 1 proton plus 1 neutron, and then hydrogen 3, 1 proton plus 2 neutrons. So that little number here after, that's our mass number. So that's how we can tell what isotope it is. So almost all elements have at least 2 different isotopes. Some of them have just a ton. Some are stable, others not so stable. And that's why if you look at that bottom number on your periodic table, that average atomic mass, it's closer to one number versus the other. So like if you look at carbon, carbon is 12.01. Well, that's because this is a stable isotope, and there's a lot of this. More of this occurs naturally, partially because it is stable. And we can guess that by looking at our periodic table. A little review on notation. So a couple of things you're going to see a lot of. One, hyphen notation, so element name, mass number. The other one then is nuclear chemistry, so how about nuclear notation? Mass number up top, atomic number on bottom, symbol afterwards. This is what you want to see. That makes this super easy. Everything is given to you. You got protons plus neutrons here. You got protons here. If you want to find neutrons, just subtract top from bottom, and you have your numbers of neutrons. Alright, so this is nuclear chemistry, so we're going to talk about radioactivity. Some isotopes are unstable, meaning either you have too many protons or too many neutrons. There's not this perfect ratio. All elements number 84 and up have radioactive properties, and then there's some small ones too, like that last slide had carbon 14. Carbon 14 is radioactive. Here, that hydrogen 3 tritium is also radioactive. So how do we know if something's going to be radioactive? Well, we have something called the band of stability, and isotopes at the edge of this band are radioactive. So the black line here, that's your 1-to-1 ratio, so like 82,82 on your graph. So 1-to-1 ratio, notice as the element gets bigger, that ratio starts to veer off from that 1-to-1 ratio, and we end up with more neutrons than we do, and this should say number of protons. I cut off my picture. But the black spots here, those are all stable isotopes. The ones in blue undergo something called beta emission. The ones in orange undergo something called positron, which is the opposite of that. We'll talk about these here in a second. You have alpha emissions in yellow, fission in green, all things we're going to talk about here. So what determines if it is going to be radioactive? It is that neutron to proton ratio. So for small elements, you want to be stable, or for a small element to be stable, 1 neutron for every proton. Bigger atoms, bigger isotopes want 1.5 neutrons for every proton. What this does is those neutrons aid to increase the nuclear force, or the force holding together the nucleus in larger atoms. Because you got to think, you got a whole bunch of positive stuff. Neutrons don't have a charge, but protons do. All of that positive stuff wants to repel, so you need something to hold them in, and that's called the nuclear force. So you pack some neutrons in, spread some of that positive force out, or that positive repulsion out, plus you have that nuclear force holding them in. That's how they stay stable. But you start making that nucleus bigger, so you get the 84 protons, and then you have 1.5 times that neutrons. It doesn't matter. You just have way too much positive repulsion in there. So how to use the band of stability? Well, so again, neutrons, protons, it'll always be like that. If you are off the band of the if you are off of this band, it doesn't exist in nature. At the edge, you are unstable, and if you're on the band, you are stable. So how these things are going to become stable is they're going to release particles. And we're going to talk about alpha emission, beta emission, and then gamma rays, which is something you might have heard of before, to become this more stable element. And a lot of times it does end in lead. If you are a radioactive element, this happens spontaneously. We don't have to, fire a neutron at it or give it a charge or anything. Like, it just does this to become more stable. Everything in nature wants to be as stable as possible. All right. We call this process transmutation, which, way back in, people were trying, I guess, the first chemists, first alchemists, were trying to turn different elements into gold. It was their end game, and we call this alchemy. And we know this isn't possible, but now we talk about nuclear chemistry. We know this kind of is possible. It may not be gold, but we can turn one element into another. So atom of one element changed into atom of a different element. So during these changes, these particles either absorbed or released, and then you also get this energy as gamma rays, or in the case of a nuclear explosion, you also get just whatever kind of energy you want to call it. You get light, sound, all different types of energy as well. All right, types of radioactive decay. The three we're going to talk about, and there's others like that positron, and there's a couple more I can't think of off the top of my head right now. But the three we're going to focus on, the first one is an alpha particle, and that looks like a helium atom. Actually, it's a helium ion. It's charged, but we care that it has a mass number of 4, atomic number of 2, so you may see it written either way, so the Greek letter alpha. This solves the problem of having too many protons. So what we're going to do is we're going to get rid of 2 protons when we release an alpha particle. Beta particles, so you'll see it as 1 over -1 e, so it's an electron, or you may see it as a beta minus. This solves the problem of too many neutrons. So what we're actually going to do is this kind of adds a proton. In the easiest way to think about it is this ends up adding a proton because of this -1 down here. But really what's happening in terms of kind of the physics, the chemistry behind it is a neutron is actually split into an electron and a proton. Crazy to think about, but that is what's happening. The proton ends up being kept, the electron is ejected, plus we lost that neutron in the split. Gamma decay, so Greek letter gamma looks kind of like a Y. All this does, this solves the problem of too much energy. So it doesn't change our number of particles, it just brings us down to lower energy. We usually do not show this in reactions that we're going to write. So summary of types here, talking about damage, alpha particle, least to worry about here. You could stop this with a piece of paper. Beta particles, I've heard it explained as you could stop with a piece of aluminum foil. Gamma particles, you got to stop with like a 10-foot concrete wall. So tons of energy here. These other ones just kind of minuscule in comparison. Again, helium nucleus, electron, and then this is just a bunch of energy. Different ways you'll see notation. All right, here's the slide we're talking about here. Gamma, most penetrating, ones that, highest energy. These are the ones we worry about when talking about radiation, radioactive materials. So altered DNA, that's never good. This is where we get all these cancer-causing things and stuff, but we actually also cobalt-60 use in cancer treatment. So if we fire gamma particles at a cancerous cell, we can alter its DNA and keep it from replicating correctly and stop the growth. Alpha, thin barrier, so sheet of paper, too big and too heavy, can't travel very far. Makes sense. Much bigger than the rest of them. So remember, electrons super small in comparison to a proton and a neutron. So with 2 protons and 2 neutrons, they're much, much bigger. But when inhaled or ingested, could be dangerous. Beta, clothing, wood, aluminum, sheet of aluminum will stop that. Again, dangerous when inhaled or ingested, but overall not so bad. All right, nuclear reactions. Remember, law of conservation of matter, law of conservation of mass, it has to equal the same. So we have radon 226 here undergoing alpha emission, so releasing an alpha particle. And then what are we going to get? Well, we're probably going to get some gamma rays in here just because we got to lower the energy. But remember, law of conservation of matter, so this side must equal this side. We look and, okay, well, we end up with 222 up top, 86 on bottom. Well, if you look, top's equal 226, bottom's equal 88, and again, gamma not shown.